Well, ready or not, we're going to. So welcome. This is week 2. Today's January the 16th. And I think last time I promised you that during the break I would pull up a video and show it to you. And so I'm going to do that right now. So this is me. Oh, wait, you can't see it. Hold on. Still not there. This is on the cliff, the Lehigh River. Woohoo! So, why would I show you that? I mean, besides the fact that I told you how I went scuba diving after and found all sorts of hidden treasure. What does it have to do with statistics? Think more about the hidden treasure part. So I told you how my friend was standing on the top there, and he's the one who took that video. And then he promptly dropped my phone in the water. This was the Saturday when they have the water level high for rafting. So I went back on Monday when the water was lower, and I found my phone, but I also found a bunch of other stuff. Treasure, you might call it. 4 knives, a couple of watches, sunglasses, a GoPro. So I made out about retail value, $700 or $800 on the whole adventure. So what does that have to do with statistics? Well, yeah, go ahead.
Maybe you get that just like how you lost your phone, others might have dropped something in it, and like there's a possibility that others did as well. So you went for it and
Okay. So yeah, I went back looking for my phone, but I found a bunch of other stuff. And in hindsight, and I guess that would now be foresight, this cliff that I jumped off is pretty popular. It's only like 15, you saw it's not that high, like 15 feet. And lots of people stop there and jump off and lose stuff. So if I had gone back with my scuba gear and just said, I'm going to just search the whole river, how long is that going to take? Forever. Am I ever going to find my phone? Probably not. But I had information where I lost the phone, at least general area, and lots of other people are doing that sort of thing too. So if I were to go out and try and find buried treasure or lost treasure, I would take what I know and use that to help improve my chances of finding what it is that I'm looking for. Okay, so there you go. There's the spiel on why it was relevant that I showed you that video and told you about all that. So I'm going to ask you guys a couple of questions. See how much you paid attention to the videos this week. So first of all, what is a characteristic of a population called? And you can just type this right in your phone or your computer and send it in. So there's about 65 of you guys out there, and 10 have responded so far. All right, so we're just going to look at the response history for the 32 that have answered so far. A lot of things: age, structure, census, demographics, numerical, parameter. Okay, the right term is parameter. Looks like a bunch of you guys got that right. And sample, size, study variable, and so forth. So of 32 people that answered in the allotted time, majority of you got that right, which is good. I want to just come over here and make sure that everybody understands how this is, how this works, how statistics works. So here's the big picture. And when you're struggling with the details and questions that you might have in this class, or when you're starting to apply statistics to other classes, you should step back and say, okay, how does this fit into the big picture? So we are interested in populations. Why are we interested in populations? We want to know about the characteristics of the population. Why? So we can sell them stuff, right? We have to make decisions. You guys are, this is a business school. We have to figure out what it is these guys are interested in and what size they need. Like shoes. Everyone's interested in shoes. Everyone wears shoes. Not everybody, but the United States, most people wear shoes. So if you're going to make shoes, you need to know about the characteristics of the foot size of people in the United States or in the world. And so characteristics are called parameters. And they're things that are so important that we use Greek letters. Mu, for example, sigma, pi, theta, and so forth. Parameters are very useful because they, well, if we know what a parameter is, then we know almost everything we need to know about the population. If we know what the distribution is and the parameters, then we know everything we need to. But what characteristics or what qualities do parameters have? Well, there's three of them. The first one is that they're fixed, so they don't change as long as the population doesn't change. The parameters are fixed. Second one is they're unknown, at least for large populations. That's going to be true. And finally, they're unknowable. So not only are they unknown, but there's no way to find out what they are absolutely. So what is it about parameters that makes them have those characteristics? They're fixed, they're unknown, they're unknowable. You think about a population. Population is a large group of people, or doesn't have to be people. It could be insects or animals or anything you might possibly think of. And for a large group, how long would it take you to find out the characteristic that you're interested in? So for example, if you wanted to know the bank account content of all Americans, how much does everybody have in the bank, in their checking account or their savings account or whatever it is? How would you find that?
By taking a census.
Okay, so a census is a sample of the entire population.
And
right?
by the time you would be done with it, the information is probably changed.
But okay, so that's the point why this is unknowable. If I want to find out everybody's bank account content, I can either try and get the banks to tell me that, which is never going to happen unless I'm maybe the federal government and Congress makes some law that says you have to tell the government. Short of that happening, how else could I get it? I could ask people, And so how long does it take to do that? It takes a long time. And has anybody accessed their bank since yesterday? Has your bank account balance changed in the last day? Yeah, so it's changing all the time. So even if you could ask people and they did tell you correctly, by the way, who wants to tell me how much they have in their bank? Don't tell me, but how much? Who wants to tell? Nobody wants to tell that information, right? So if you ask people, they were going to probably say, mind your own business. And you say, oh, but it's for science. You say, what science? Mind its own business. I'm not telling you. Or I don't know, maybe you say, okay, I'll throw some randomness in there. There are ways of dealing with that sort of thing. But to find out what the characteristics are, what I'm telling you is that it's impossible to do. You can't know what they are for any population that's interesting. Let's say there are some small populations that are small enough that you could find out the characteristics that you're interested in. So what do we do then instead? We take a sample, and the sample is going to allow us to make statements about the parameters. And it has its own set of characteristics. And so what are the characteristics called for a sample? We'll just let people see what everybody else is saying. Statistics, well, that's the name of the class. Statistics, lowercase, okay, maybe that. Everybody's saying statistics. Standard, all right, let's. So random chosen, standard, statistics, variable. So it turns out that the characteristics of a sample are called statistics. And they're denoted by just regular letters. I don't know, what's that alphabet called? The one we use in English? X bar, S, P, T, and so forth. So we use the statistics in order to make statements about the parameter values. But in order to do that, we have to know about something called probability. And probability is just the study of uncertainty. And we will talk all about probability next week and uncertainty. And next week will be very interesting, so you definitely don't want to miss class next week. But the way probability works, or the way this inference works, so going back this direction to make statements about the characteristics, we have to use what's called inferential statistics. So there's that word again, statistics. So there's a couple of different approaches to statistics. One is the classical or the frequentist approach, and that says let's make an assumption about the characteristics of the population. And once we have an assumption, then what are we going to do? We have some idea of what these numbers are, what these parameter values are. Then we're going to go collect data and see if the data supports that. Right? So that's one approach to statistics. And if you think about it, it's actually kind of backwards in some regards, because you're saying, here's my hypothesis. Now I'm going to chase that all over the place until I find some data that supports it. Okay, so people who do this generally are going to say, well, here's the hypothesis. This is what I think is going on. does the data support it? If the data does, I'm going to publish that, get everybody to agree with me, and then I'll be famous because I proved this hypothesis. And if I don't find data that supports it, then what am I going to do? Well, the incentive structure is all messed up. I'm just going to ignore the first set of data, and I'm going to go and find new data. And if that doesn't support the hypothesis or the theory that I've got, I'm going to do it over and over and over again until I find something that supports my theory. Okay, so there's all sorts of data that gets ignored and thrown away that is contrary to somebody's theory, but that's not what they're interested in proving. So, so there are some criticisms against that type of statistical inference. And there's another way to do it that is called the Bayesian method, which says, let's just collect some data, and based on the data, make statements about the actual values of the parameters. Now that's contrary to what the classical people say, because classical statisticians, again, say the parameters are fixed, they're unknown, and they're unknowable. So it doesn't make sense to say there's probability associated with them being in a certain range and so forth. Bayesians, on the other hand, say, yeah, all that's true, but we're going to treat the parameters like they're random variables because they're unknown to us and we can't be certain about their values, so we're going to treat them like other things that are unknown and have uncertain values. So random variables. Okay, so when you get into statistics, you're gonna collect these things, characteristics of a sample, and then you're gonna say how likely is the value that's observed based on the laws of probability, and that is going to allow you to make statements then about the parameter values. And so when you get bogged down in the details, you just have to step back and say, where do the details fit in? They fit in over here by saying x bar, what's the distribution of x bar? And we'll talk more about that a little bit later. But you can think of this big picture approach in just about any setting, whether you're doing Bayesian or classical statistics or frequentist statistics. Okay, so one other question then. This is probably not one that you, and we'll see how you guys do on this one. What's the characteristic of an individual called? So we got a population, that's everybody. We have a sample, that's a subgroup of the population. And then we've got the individual members of the population or the sample. And those have a name as well, or the characteristics of those things have a name. All right, so we have 18 responses. I guess I'm just going to assume that those who don't respond don't know the answer to this question. So let's look here and see what we have. Attributes, data, evidence, observation, traits, variable, oh good. So it's actually called variable, and some of you got that right. I did not mention that anywhere else, so that's good that you found that. Okay, so when I was in graduate school, I did a PhD at Duke University, and I was married at the time and still am married to the same person. And after you hear the story, you might wonder how we got through it. But so I was going to Duke, and my wife worked for a year or two, and it was a PhD program, takes forever, and she kind of got bored with work, and so she said, I want to go to school too, and so applied around, and she got into UNC, and And so she shows up first day of class. Well, she a bunch of different classes she had to take, but in her statistics class, they said, "Look, all you guys are studying city planning, which is a good field. We're in it too, and the teachers were thought it was great. But they said, if you're interested in earning a lot of money, you probably should major in something else." And they're like, "What?" I mean, as long as it's closely related to city planning, then maybe they would consider it. And they said, well, just tell me, what do you think the average starting salary is for geography majors at UNC? Okay, so I want to ask you guys that same question. Remember, what did geography majors do? They drive Uber cars? No. Well, they got to know locations, cities, streams, lakes, capitals, all that stuff. So how much and I shouldn't make jokes. I was not making a joke at Uber drivers. I apologize if you know any Uber drivers and you're offended by that. Or maybe if you're planning on doing that. Alright, so we got about 40 here. So I can see what you guys said. 40,000, 70,000, 37, 45, 0. 250 in the video, so someone makes videos, and is that 250? Is that what you're saying? 25K, 250. So it means 2 people watch the video. Why? The correct answer is 250,000. So for UNC, starting salary is about $250,000. Why is it so big? You guys didn't know that if you know all the locations of capitals and mountain ranges and borders and all that stuff, you can make that much money? Like Google Earth, they all go and work for Google Earth, and so they make. I'm just kidding. It's not true. Why is it? What's the case? And is this something that's everywhere? In other words, if you majored in geography at Drexel, could you expect that kind of money? No. What happened at North Carolina? You had Michael Jordan majored in geography. He left as a junior and went to the NBA and played 3 or 4 years, and then he had contracts from Nike and Gatorade and McDonald's and whoever else, and they were paying him $60 million a year when he finally graduated a few years later. So he's making $60 million. Everybody else is down here at like 20 to 30,000. And so this point here pulls the average value up to $250,000. So is that so? What's going on here? Why do we care about that? Or what do we need to make sure we avoid, or how can we avoid this? Okay, so it's definitely is it an outlier? I don't know. Did Michael Jordan, he traveled like every week. He was at a new location, and all that geography knowledge he had probably came in handy. So you could make an argument, but yeah, I think it is an outlier. And so you could just throw it out and say, well, let's just calculate the mean, which is x bar, the summation of the x's divided by the sample size. That's one thing that we could do. But is that information useful? Is it? I mean, he is part of the population after all. So what else could we use that doesn't just throw the data out? The median. Okay, what does the median tell us?
Kind of the middle value.
That's the middle value. Exactly, the point in the middle. So wherever that turns out to be, says sure, you can have 60 million in the sample if you want, in the population, and that's going to pull the average way up, but it's not going to be any more effect or have any more effect on the median than say 100,000 would, or 200,000 or whatever. So the median is something that's often used in place of the mean. Can you think of any other examples where the median is more useful or more, I would say useful, but more indicative of the typical data point? Because that's what we're really trying to do with the mean and the median, is we're trying to say where's the middle, or where's the measure of center? Where's the center of this distribution? And why do we care about where the center of the distribution is? So we can tell if someone or some individual or observation is bigger than the average or smaller. And how close is it to the center? So we want to know about measures of center. We also want to know about measures of variation. So we can say, well, if it's 20 units above the mean, is that big or is that small? We can't answer that question unless we know how much variation there is in the data. And all these things will become more clear as we move on. But what's another example of where the median is used instead of the mean? House prices. Bill Gates, I don't know if this is true or not, but I heard that he bought a whole neighborhood outside of Seattle and tore down all the houses and built his $200 million house or whatever it cost. So you get a few of these houses on Long Island and downtown New York City and the penthouses and so forth that are super expensive. You don't want to consider those when you go to decide how much you need to have in order to buy a house when you graduate from college and graduate school or whatever, right? That grossly pulls the average up, and so be a little bit careful about that. Okay, so I'm going to ask you one more question, and actually it's 4 more questions all at the same time, and we're going to look at Excel, and we're going to see how to deal with raw data. Okay, so what I want is, before you send anything in, whoever wrote that needs to put more in than just that, and that, don't put that either. So what you need is the answer to 4 questions. How many hours per week on average do you spend on homework? How many hours on a week do you spend watching television, like YouTube, Netflix, Hulu, and so forth? What's your GPA? And finally, how old are you? And I want these written in this format, if you wouldn't mind. So I don't do any homework, so I'll put a 0 and then a comma, and I don't really watch TV, and I don't have a GPA, and I'm not alive yet. Okay, so just put it in like that. Don't write hours or days or GPA or anything like that. Just put it in just like that. So those H's, don't do those H's, because I'm going to have to go and delete those in just a minute. We're going to pull this down, and then I'll post this on the web, and I won't put any identifying sort of information, so no one will know what your GPA is or how much time you spend doing homework or whatever. how old you are. All right, let's see how many we got now. $52. Okay, so I counted 65 people here today. So we'll give you another couple seconds. Get your responses in. All right, anybody else still planning to submit? You think about it. All right, we got 59, we'll take that. Okay, so here's my data. What's the first thing I need to do? Before I can manipulate any of the data or view any of the data, I have to clean up the data set. Clean up the data. And what does that mean? That means I just simply have to make it so that that I can do stuff with it. Okay, so I'm going to put in homework, comma TV, comma GPA, comma age, and then I'm going to try and separate these things. How can I separate all these things? Well, if I have Excel, which I do, I can go to data and then text to columns. Actually, let me select everything first. So select all the data and then go text to columns, delimited, next, comma is all I want. I don't want space, I don't want tab, just commas. And then I'm going to say next and then finish. Okay, so it looks like this first person did not put in commas, so I'm going to have to fix this up. And turns out if you're going to do data analytics, about 90% of what you spend your time on is fixing data, cleaning up data, making sure you've got stuff that is going to work. So 20, 3.87. 2 hours on TV and 20 hours on homework. All right, so what other problems do we have here? Somebody said 10 hours. They didn't put the other ones in there. We'll just leave that as is then. Not quite sure what happened with that. Let's just put 22, 3.6, 15, and 11. Okay, 3x, 3.x. I don't know what that means, so I have a couple of options. I can either ask the person who said this to tell me the real number, or I can throw it out, or I can just say, oh, x, that means anything I want. So I'm just going to leave it at 3.0. And you know, typically, you know, if I were really doing this, I would probably just say, just throw that one out. Yeah, okay, let's just do that. We'll just throw that one out. 8 to 10. What am I supposed to do with that? Call it 9. Could do that. I could, again, petition for someone to fix that. At least I have a range on that one instead of like with 3.x. I know it's in the 3s, but you know, I guess I guess I could do the same thing and put as 3.5. Should we do that? Yeah, let's do that. That's generous, isn't it? Okay, so 0 hours. I got to get rid of the h. 12. And here again we got 18, 3.1, 4, and 7. All right. And then I'm not sure what this is. I'm just going to get rid of it. And I'm going to get rid of this one. Okay, so that'll make things look a little bit nicer. And now, okay, so I've got the data. This is my raw data. It's finally ready to look at. What's the first thing I'm going to do? Let's pick one variable, say age. We want to understand what age is like in this class. Okay, so the first thing I want to do is do some sort of organization, right? And usually the first thing we do is sort the data. So here's age. I actually want to sort all of the data. I want to be very careful that I don't sort just the age. If I do that, then I lose all of the connections with the other data. So I highlight all of the data, and then I'm going to say sort by age. And be careful, because look. Oh, it did select it all. Okay. So sometimes, if you got a blank row in here, sometimes it will only select the first part. So make sure you got all the data. And then we'll go sort by age, smallest to largest. Okay, so here's 18. We have two 18-year-olds, a bunch of 19-year-olds, a bunch of 20-year-olds, 21, 22, 23, 24, and 26. So I know what the minimum and the maximum are. I could use the functions mean. Let's see. Sorry, the function is called average. So if I type average and then select all the data, see the average age is 20.38. The sample standard deviation is going to be equal to stdev.s. Select the same data. We see a mean of 20.38, standard deviation of 1.44. So this is age. These are summary statistics. I can find the median. Median is, so just type median, and median is 20. Okay, so those are some of the numerical summaries I can look at very quickly. Does this help me understand what the shape of the distribution is? No, I have just the mean and the standard deviation. The mean and the median are pretty close to each other, so that suggests that there's going to be some symmetry. So that does help me a little bit. But what could I do to look at, say, a dot plot for this data? Well, first thing I need to do is find the count, or the frequency. We'll call it count. And I'm going to say the first one is 18, and there's a couple of those. But here's the first 18, and the second one is 18, so I've got two 18s. And then I start over at 19, which is 1. I could go through the table and find all of those numbers and just type 1, 2, 3, 4, 5, 6, 7, 8, and so forth. But the easier way, or the better way to do this, is to use the if statement, the if function. And so if D3 is equal to D2, if that's true, then I want to get whatever the count is, I want to add 1 to it. And if they're not equal to each other, then I want to start over counting again. Okay, so here I've got 2, and I'm going to just copy and paste that in, and you can see that here I have 18 and 19 are not equal to each other, so I'm going to put in a 1. All right, so if I do this for all the values, I can very easily see that there are 11 19s, there are 23 20s, 11 21s, 3 23s, 1 24, and 1 26. Okay, so if with this age and the count, I can now insert a dot plot, and you can see then that the shape of this thing is actually fairly symmetric. I'm going to change this so that we have, instead of going from 0 to 30, let's change it to 17 up to 27. Okay, that's good. Okay, so this is called a dot plot. The height of the stack of the dots tells me basically the frequency, and I can see very quickly what's going on with the data by looking at this plot. Now, there's another plot called a histogram, which is very similar to this, and Excel doesn't really do histograms. I don't know. I heard that they finally put it into 2017, the latest and greatest, but I haven't been able to find it and make it really work. There is, under the Data Analysis Tool Pack, a histogram function, and that doesn't really make a histogram. What it makes is, let's go over here, we got age, I didn't put the label in there, so just say OK. But what you can see basically is a frequency distribution. So here's the bins from 18 to 19.14. There's 2, and so forth. So this is not really a histogram. You could use this to make a histogram, but it's basically the same sort of thing as what we did here, except for, let me just insert things. Frequency distribution, so we've got age, and it starts at 18, and then 19, 20, 21, 22, 23, 24, and 26, I think it was. That look right? And then the frequency just says, well, let's go in and count these things. How many 18-year-olds do we have? 2. How many 19-year-olds are there? There's 11. How many 20-year-olds? There's 23. What else do we have here? So we have 11, 3, 3, and then 1, 1. And so this is a frequency distribution. It says, let's count the number of observations we have in each of these ranges. And you can think of 18 being anything between 18 years and 0 months, or 0 seconds, up to 19 years and 0 seconds, so not including 19. How do you get Data Analysis Tool Pack? Yeah, so you go over here to File, click on File, and then Options, and then Add-ins. And then come down here, it says Excel Add-ins, say Go, and then you should see Analysis Tool Pack. So click on that, say OK. I've already got it loaded. You might have to restart Excel before it shows up, but you get that under the Data tab. Okay, so frequency distributions are important. They help us to do lots of different things. And one of those is to calculate what's called the relative frequency. What do you think relative frequency means? It's just the proportion that goes along with the data point. So we would say, first of all, how many data points do we have? So if I sum all of these things, I'll see that we have 55 data points. So to get the relative frequency, we're going to say, give me the frequency, and then divide that by the total number. So we have about 3.6% of the class is 18 years old. Right, so I want to get the same thing for all of these values. So I could do the same thing, just say 11 divided by 55, and that will give me 20%. Okay, 20%. That's not what I want to do. Hold on. Okay, but can I just copy this and paste it the rest of the way down? Or rather, if I copy this and paste it here, what am I going to get? I'm going to get 0, or sorry, something divided by 0, which is not good. Although Excel says divided by 0 factorial, which is 1. So that's not what they really mean, is it? So what's it doing? It's taking the denominator and using a relative reference. What's a relative reference? So it says this cell I3 is going to be H3 divided by H11. And so these are relative references. So relative to I3, you're going 1 to the left for the numerator, and then you're going for the denominator 1 to the left and 8 down. And so we don't want a relative reference. Actually, we do want one relative, but we want one absolute reference, and that is here on H11. So if you put a $H, $11, that says instead of a relative reference, let's use an absolute reference. So it doesn't matter where I copy and paste this to, it's always going to use H11 in the denominator. Okay, so if I copy this, paste it here, I get the same thing, except for now that there are dollar signs. But most importantly, if I put this all the way down, I get the denominator is always going to be this 55. Okay, so that's a useful Excel trick. You need to know about that if you're going to use Excel at all. Oh, and by the way, I am about this close to getting Excel to work with the Lockdown browser, and if that happens, then you'll be able to use Excel on the exam. So don't write off Excel. Make sure you're learning how to use it, and earlier is better than later. Okay, so relative frequency, that gives me the proportion. And so I could treat this like a probability. I could say if I were to randomly select one person from class, what's the probability that they are 23 years old? And that would be 5.4%, or 0.054. Same thing for all these other ones. So I can look at this and say, well, 41% of the class is 20, 20% is 21, 20% is 19. And that, again, is another way to look at this and get numerical values that tell me about how the probability distribution, or rather how the random variable is distributed. Okay, so this is an important concept. We're going to use this quite a bit when we talk about probability distributions next week, and or at least something very similar to this. The next thing that we need is the notion of the cumulative frequency. And the cumulative frequency is what? What does it mean to accumulate stuff? You guys are all in college now, right? Yeah, okay. That's what I thought. But when you were not in college and you still lived at home, your parents would do things. I mean, I do this to my kids all the time. I do stuff and they remember it and they add it up. And then at some point they say, look, here's the laundry list. You did this and this and this and this and this and this. And now I want to go and do something with my friends. And because you did all that stuff, you have to, pay me back, sort of thing. You guys all did that, right? Well, you should have, but if you didn't, that's okay. Your parents are doing the same thing to you. So just in the future, they'll say, look, this. So cumulative means you're adding stuff up as it goes, and then you can look at it and say, okay, what's the probability, or how many students are less than or equal to 22 years old? You don't have to go in here and say, well, I've got 2 plus 11 plus 23 plus 11 plus 3. The cumulative table is adding that up as you go. So what are we going to do? The first one is going to be just 2. And then we're going to say, give us the next value plus the previous value. And as you add all these things up, you see that the total number is 55, which it should be. Okay, so relative cumulative frequency, what do you think that is? The percentages added up. All right, so we're just going to copy this and paste it, and copy this and paste it, and we'll see if we did that right. If the probabilities sum up to 1, then we did that right. Now I told you that in class we're going to be covering stuff that is either extra important or maybe you didn't see in the videos. I think this is in the videos, but this is very, very, very important, this idea of cumulative frequencies and cumulative probabilities. We'll build on this next week when we get to probability, and you will find that having the cumulative probability distribution function, as it's called, is going to be, well, your best friend, maybe your second best friend in life, eventually, down the road, and you're going to use it all the time. So if I want to know what's the probability that if I randomly select someone from class, I want to know what's the probability that they're less than or equal to 22 years of age. All I have to do is look on this table. Look at that, it's 90.9%. And that just comes from adding up all these numbers. There's 50 of those, 50 divided by 55. So if I want to know the probability that somebody's greater than 22 years old, how am I going to find that? Again, using this cumulative relative frequency. I just take this value and subtract it from 1. So 1 minus 0.9099 is 0.09, so about 9%. About 9% of the class is it's greater than 22 years old, and 91% is less than or equal to 22 years old, or less than 23 years old. Okay, so again, this is something you'll see again over and over. You need to embrace it and figure out how to use it because it's going to be very important. Okay, let's take a break for 10 minutes. We'll start back up at 5 after the hour. If we want to look at 2 variables at once, what tools do we have at our disposal? And whenever we talk about tools, generally you're going to be thinking numeric and graphical. So what graphical tool do we have if we want to look at 2 variables? So the gentleman in the front row said we can plot more than one set of data on the same graph. Okay, we can do that. What's the graph called? Scatter plot. Scatter plot's a good one if we're going to use just two variables. We want to see the relationship. Like bar graph. Okay, so bar graph is usually done with just one variable. Line graph, on the other hand, is closely related to a scatter plot. So homework and TV. Do you think those things are related to each other? Maybe. I mean, could be. I don't know if they are not, but in theory, if you watch a lot of homework, if you do a lot of homework, how much TV are you going to be able to watch? Less? Okay. That's generally what you would think. I guess it's possible for some people probably do it, to do both at the same time, think they know how to multitask or something like that, so they watch TV while they're doing their homework. Anybody do that? Heaven forbid. Oh, sorry. Yes. If it works for you, fine. My daughter's always telling me I can listen to the music, listen to whatever, and do my homework at the same time, and I don't know about that, but okay. What about TV and GPA? Think the amount of TV you watch has an effect on your GPA? In a good way or a bad way? Could be good or bad, couldn't it? If all you watch is TED Talks, maybe that's good. If all you watch are Netflix dramas, then who knows? Okay, so let's look at TV and GPA. If we come over here to insert and then scatter plot, we can see here's the basic relationship. I'm going to try and change the format of the axis. 4.5. I don't know. This calls one minor, one major. I don't know which one's which, but none of these seem to really match up. So I guess we'll leave it automatic, which I don't recommend doing with Microsoft products. If you let them, they will try and think for you. And but what do we have here? This point out here, somebody who watches 50 hours of TV a week, their GPA is 2.5. Is that an influential point, do you think? So what's the relationship? If you had to draw a straight line, what would the straight line look like that best fits this data? Well, yeah, it probably would. It would be pulled down by this one a little bit. So if we got rid of that data point, you would have something that goes up a little bit more. Okay, but it doesn't look like there's a real strong relationship here, does there? So scatter plots are useful tools to get a basic idea of the relationship. And we're going to actually care quite a bit about the relationship between variables towards the end of the class, because oftentimes if you know one variable, then there's some information contained in that variable that helps explain another variable. Now, it's not always the case, but that's the type of thing we're going to look for. We want to understand information, right? We want to know where to look for the hidden treasure in the river with our scuba gear. And if we just kind of randomly go out and look, chances are not that good. But if we can use other information, where did I lose my phone? Where does everybody else jump off the cliff? That's useful information. That can really help. Okay, so that's what the idea behind the this scatter plot tool is. All right, so let's move this thing out of the way. So that's the graphical representation. What about the non-graphic, or the numeric? I'm going to just, I guess we'll leave that there. How can I measure the strength of the relationship between these variables numerically? Well, there's a function called there's a notion called correlation. And if I say, what's the correlation between TV and GPA? I can use this function that says put the first column, comma, the second column. So there's TV and GPA. And I see that the correlation, is that what we plotted? That's what we plotted, right? I'm confusing myself. No, this is age and so we didn't have GPA and TV, but this correlation is GPA and TV. So let's redo this plot because I think I did the wrong one. Nobody caught me on it. Nope. Okay, yeah, that is the right one. All right, never mind. So the correlation is negative 0.24, which is actually a little bit stronger than I would think by looking at that data point or that plot. But if we take out the plot, the point that has somebody watching 50 hours of TV, so let's just delete that real quick. You can see the correlation changed from negative 0.24 to negative 0.06. So that 1 point's very influential. And maybe, maybe it's an outlier even. I'll just put it back in though for now. But I would look at that and say, yeah, it looks like there is a negative correlation. Now, whether it's significantly significant, statistically significant or not, that's another question for later in class. But how many pairs of variables do I have here? Now, how many variables do I have? There's 4 variables. So how many pairs do I have? I have homework and TV, that's 1 pair. Homework and GPA, that's another pair. Homework and age, that's a 3rd pair. TV and GPA, that's a 4th pair. TV and age, that's a 5th pair. And GPA and age, that's a 6th pair. So there's actually 6 different pairs of variables that I have here. So if I just calculate the correlation between 2 of them, that doesn't tell me everything I need to know about correlation. So I could go through and use this function 6 different times. However, that's kind of tiresome. So instead I'm going to go to the data analysis toolpack and click on the correlation function, and it says give me the input range. So I'm just going to select the 4 variables, and then I'm going to say does it have labels in the first row? Yes. And it's going to give this to me in a new worksheet. Okay, so here's what I get. Blow this up. So TV versus homework has a 47% correlation. So is that's of all these that we see here, that's probably the strongest correlation. So what does that mean though?
Spend about the same time doing both.
No, that's not it. So correlation, think about correlation. If 2 things are correlated, it means as one goes up, what does the other one tend to do? It also goes up. Now, I would think that homework and TV would be negatively correlated. I mean, the more time you spend on homework, the less time you have for TV. But according to this, that's not the case. So let's look at the scatter plot for this one. And there you have it. So we've got 20 and 50. So which one's which? 50, I guess 50 is TV, right? So somebody spends 42 hours watching, no, 42 hours on homework and 35 hours watching TV a week. And this person spends 20 doing homework and 50 watching TV. And you can see these 2 points are probably responsible for most of that upward trend. So we'd have to ask the question, is there an intersection between those things? Whoever's doing 50 and 20, or is that doing both? Because 70 hours a week, I mean, you know, how many hours are there in a week? 168. There's plenty of time to do that, so I guess it's possible. But what else do you do? I don't know. Okay, so we've got this correlation matrix, and this is a very useful function to know how to use. And so we look at this and say homework and age, that's pretty low correlation. Age and TV, pretty low correlation. GPA and age doesn't really seem to have any sort of effect. So you would say age is not significantly related to these other variables. So it doesn't help me understand how much time somebody's going to watch television or how much they're going to do homework if I know their age. And we'll talk more about these things later on. But that one right there does kind of surprise me a little bit. But I don't know. Maybe that's just the world we live in now. People are watching a lot of television and doing a lot of homework. What's that?
What was it in the other class?
I think it was negative. It was, I don't remember. It was quite a bit less. I'd have to look. Oh, but wait a second. Now hold on. I answered my own question just thinking about this for a second. When you do homework anymore, you're watching videos, right? So you guys were including like all the videos from this class that you're watching. So that's homework and watching videos. So there is an intersection. Must be. That's got to be it. Okay. So what else can we do with the data? So we get a pretty good idea of how these things are related to each other. And maybe we should have done this before we looked at the correlation structure. But you guys remember the empirical rule? The empirical rule says, and there's another rule kind of like it called Chebyshev's inequality, but the empirical rule says basically if you have symmetric bell-shaped data with a mean mu and you go one standard deviation above and one standard deviation below, then you have a certain proportion of the data, and that proportion is about 68%. Okay, so that's the first one standard deviation up and down. If you go up 2 standard deviations and down 2 standard deviations, then you have how much of the data? About 95.5% of the data. And if you go plus or minus 3 standard deviations, you have almost all of the data. In fact, it's so close that oftentimes we'll say, just give me the range, and we'll treat that like 6 sigma. In fact, there's some homework problems, and I think for chapter, not this week's homework, but next week's homework, that says estimate sigma by taking the range and dividing by 6. And that's based on this empirical rule. So look for that. So this is in the X world. In other words, if X is my random variable, maybe it's IQ. We would say, what's the average? Whatever it is, it's mu. And what's the standard deviation? If you go up and down one standard deviation, then 68% of the population is going to have an IQ in that range. 95% is going to be within plus or minus 2 standard deviations. And so the empirical rule is very helpful because we can find what's called a z-score. And we get that by taking the random variable x, subtracting the mean, and dividing by standard deviation. So if I'm going to do this for mu, right, if x is equal to mu, and I plug that into this formula, what do I get? Should get 0, shouldn't I? Right, because mu minus mu is 0, so that thing goes to 0. So the z world, mu goes to 0. What does mu plus sigma go to? Well, I have mu plus sigma minus mu, that's just sigma, and I divide that by sigma, and I get 1. Same thing here, here, and here. So this formula right here gives me a standardized score, or standardized measure. What do we mean by standardized? What are the units of z? If x is in dollars, let's say. If x is in dollars, what are the units for z? Well, if x is in dollars, mu is in dollars, and sigma is in dollars. So dollars divided by dollars is what? Just 1. There's no, yeah, it just goes away. So there's no units for z. And so all this time you've been told throughout your life that you just can't compare apples to oranges. Right? You've been told that. Well, it's a lie. You can compare apples to oranges. And you can compare dogs to cats and horses to chickens and any two variables you want to if you standardize them. And that's what we're doing here basically with this empirical rule. Is we say plus or minus 1 standard deviation has 68% of the data. So I'm not going to be that surprised if I see something within plus or minus 1 standard deviation. Plus or minus 2 standard deviations, that's even more likely. But where I'm going to be surprised then is if I see z values that are bigger than 2. Because what's the chance of seeing something bigger than 2? Well, it's just this area under the curve up here, which turns out to be about a little less than 2.5%. And to see z values that are bigger than 3 in absolute value, that's even more rare. Okay, so you get a real good sense of how rare your data is if you calculate the z values. So let me move this over here. And let's just do this real quickly. Put in a few more rows. All right, so we're going to have homework.z, we'll have tv.z, gpa.z, and age.z. I don't know why I capitalize that one, not the others. But so first thing we need is the mean. So we'll find the mean, and for what variables? Homework, TV, GPA, and age. And then we'll find the standard deviation for both of those as well. Now we've already used the average function. So let's just use it again. Open parentheses. So the average for homework is 11.32, and then I want stdev.s, so I want the sample standard deviation for homework by the way, I'm moving around. I don't know if you're familiar with Excel, but you can move around very quickly if you use the control arrow keys. So it will take you to the end of a block. So here's a blank cell. So if I'm way over here on homework and I do control right, then it will stop right before the blank one. So that's how I'm getting these columns so quickly. I'm doing control shift down, it highlights everything till the next blank, and you can see that there's nothing below that. So I just want to make sure you're not getting any of the labels there. Okay, so I'm going to copy and I'm going to paste this. So now I've got the mean and the standard deviation for all the variables. Age has a mean of 20. We already calculated that, 20.38. Standard deviation 1.44. And GPA 3.35. Standard deviation 0.35. Average TV watching is 10.6. And average homework is 11.32. And there's more variation in TV watching than there is in homework. But I'm going to need all of this stuff in order to calculate the z-value. So the z-value for the first homework data point is going to be 10 minus the mean divided by the standard deviation. So that value is negative 0.19. So negative 2 standard deviations. Is that likely? Is that an extreme value? No, it's about right here, pretty close to the mean. Okay, so I want to do that for all the data points. So what am I going to do? I'm going to control C, and then I can't really control V. I can't copy and paste it. Why? Because I've got relative references. So I need absolute references, and so do I want to do relative row and column? What do you guys think? Actually, I just want to do relative row in this one, because if I don't do a relative column, then I can copy and paste to the TV and the GPA as well. So I just want relative row, so I'm going to put $2 and $3, and now I should be good for any of these things. That goes all the way down. Okay, so let's just double check to make sure that this is doing what I think it's doing. So it should be GPA, which is C2 minus the mean for GPA divided by the standard deviation of the GPA. Okay, so the relative and absolute references is something that's important. So then I can look at these things and say, are any of these very big? Well, look at this one right here. So for homework, 4.42 hours a week, that is extremely big compared to everything else. And the z-score is 4.5. So when you see something that big in a data set this small, that's a pretty good indication that, what do you think? Not necessarily an outlier, but that is something that you would want to go in and check out. But probably the distribution's not bell-shaped and symmetric. Remember the empirical rule says for a bell-shaped symmetric distribution we have all those things. Although 4.5 is going to be big no matter what, and it's going to be pretty unlikely. So do we have any other big numbers? I don't see any there. Where's the... Someone had a 50 for one of these things. Is it the same person? Oh, 35. Here it is. Okay, so here's 4.36. So yeah, you look at those things and say, those. I think the textbook technically says anything bigger than 3 is considered an outlier. And if that's how they define it, that's how it's defined. But usually you'd look at this and say, okay, that's something I want to go in and investigate. Now, sometimes you want to find the outliers. Right? If you have something that's really unusual, like Michael Jordan, you want to find those guys, get them to major in geography, or at least figure out if you can be their agent or something like that. But that's sometimes what you really want to look for. Okay, so any questions about this? Okay, any questions about the homework that's due on Thursday night? Any questions about anything else?
Quiz opens tomorrow, right?
Quiz opens, yeah, 12:01, so midnight tonight, basically. Yep. You have till Friday night at midnight to finish it, or 11:59. Okay, well, if you don't have any questions, then I will see you guys. Oh, actually, before I dismiss you, for next week, in week 3, you will see this link to an ESP experiment. It's fairly interesting, but I want you to go in, I want you to do the experiment and try and figure out what's going on, and then we will discuss it in class next week as part of probability. So we've got chapter 5 next week. We're going to do a lot of really interesting stuff in class. I don't know how interesting today was with Excel and all that, but next week, believe me, is going to be something that you want to see. You don't want to miss next week.